Hello, this is Math 2270 coming to you from the College of DuPage for summer 2020. And this lecture is the conclusion of the orthogonal trajectories discussion. Last time I left you with this problem. I hope a number of you have already solved it, but just in case you got distracted, I'll give you a moment to do this. You know what to do. Let's see how you did. Well, this was the function, the family of functions we want to find the orthogonal trajectories for. So we're going to take this and we're going to take the derivative and get this expression. So this is the differential equation associated with this family. But now we have this equation and the derivative equation, which means that C is y over x to the fourth, and so that means that we can eliminate the c. Again, that is crucial, and we write my differential equation this way, and after simplifying I have y prime is equal to 4y over x. Now what I want to do is find the differential equation associated with the orthogonal family, so I'm going to replace y prime in this with negative 1 over y prime. That's what I do here, and simplify it, and this is the differential equation associated with the orthogonal trajectory. So this is the one we have to solve. It's separable again. Here we separate the variables, and we find that this is 4y squared plus x squared is equal to 2c, and we can reorganize that, and we find that this is an ellipse with certain relationships between the major and minor axis. Here's another problem. Determine the orthogonal trajectories of the family of sinusoids. This y is equal to c sine x. You know what to do. Let's see how you did. Well, again, we're going to find the differential equation here. So we're going to, this is the family of curves. We take the derivative to get this. And then we're going to eliminate the c from this equation and this equation. So c is equal to y over sine x, and when we substitute that into this equation, we find that we have y prime is equal to y cotangent x. Now this is the differential equation associated with our original family, but we want the differential equation associated with the orthogonal curves. So we're going to replace y prime with minus 1 over y prime. We're doing it here. And reorganizing things a bit, and we end up with this differential equation to solve. Y prime is equal to minus tangent of x over y. So we work to solve this, and what we end up with is separable variables. We have to remember how to integrate the tangent. That's going to be the there's a minus that's here, and this integral is going to be a negative, so a negative is a positive. So this is going to be y squared over 2 is equal to the ln cosine of x plus the ln of c. That's where we're putting our c. Then we exponentiate both sides. Actually, we use property of logarithms here. The logarithm, the sum of the logarithms is the logarithm of the product. And so now what we're going to do is exponentiate both sides. And we find that c times the absolute value of cosine x is equal to e raised to the y squared over 2. And so that means that cosine x this is a plus or minus kind of situation. We're just going to call that another constant, playing loose with the constants. And this is the implicit solution for the orthogonal trajectories. Cosine x is equal to c1e to the y squared over 2. Now we'll talk a little bit about polar coordinates. And in the past I've spent more than half a period discussing this chart. I'm just giving you the headlines. This is all Calc 3 calculus material anyway, Calc 1 through 3 actually, a material at the College of DuPage. But suppose you have two curves, C1 and C2, and they're intersecting at a perpendicular angle. And we have these angles that are shown as theta 1 and theta 2. So those are the angles that are existing between the tangent and the the radial vectors. Okay, so we have this situation, and what we want to do is we want to have this be perpendicular, and that means that the difference between the theta 1 and the theta 2 has to be 90 degrees. And we know from our trig that that means that the tangent of theta 1 is equal to minus 1 over the tangent of theta 2. Now, one of the identities that you proved when we're dealing polar coordinates, again, not having x and y coordinates, but having r and theta coordinates, you learned in your calculus class that the tangent of theta 2 is given by r d theta dr. And so if we take minus 1 over that, instead of having this, we will have minus dr over d theta, and the r is in the denominator. So these are the key equations for doing this with polar coordinates. And so here's the hints. Hence, to find an orthogonal family of a given family, we proceed as follows. Calculate r d theta dr. So we calculate this for our given family. And then we replace that by its negative reciprocal, which is dr over r d theta, and there's a minus sign there. Then we solve the differential equation. The family of solutions of this new resulting differential equation is orthogonal to the given family. So this is the thing to memorize and be able to use in solving the problem. So let's do one. Here's a problem for you to do. I should have put a little box here, but you know what to do and when to do it. Let's see how you do. Well, so here's our equation in polar coordinates, r and theta. If we take the derivative here, we're going to get dr d theta is k, and the derivative of the secant theta is secant theta times tangent theta. That's like a Calc 1 kind of thing. And so now we have the original equation and the differential equation, and we know that k is equal to r over secant theta. So here is k secant theta, so we're going to replace that by r. And so we have dr d theta is equal to r tan theta. Now, what we need to compute is r d theta dr. Well, d theta dr is 1 over dr d theta, so we get 1 over tangent, and when we multiply by the r, this r will cancel, so this expression is 1 over tangent of theta. So now, the differential equation of the orthogonal family is, we take 1 over theta, but instead of having r d theta dr, this is minus dr over r d theta. So this is the differential equation we're seeking to solve. The variables separate, and I show a little bit more detail than the note shows here. So we go from here, these are separable variables, we integrate. On this side we get minus ln of r plus c. On the other side we get the integral of the cotangent is going to be the ln of, it should be the absolute value of sine theta, but we'll just leave it by sine theta. And then what we're going to do is exponentiate both sides. We're going to play loose with constants again. Now this minus means this is the same thing as minus ln of r, but that is ln, and then you can put that minus up there, that is 1 over r. So you see this means that this is a new constant c times 1 over r, and this becomes just sine theta. And so we can multiply both sides by r, and we get this. R sine theta is equal to a constant is the equation of the orthogonal trajectories. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care. of yourself and of each other. May God bless.